more. Professor Umesh Mishra has over 1,000 papers and 100 patents. So let's give a round of applause and welcome Professor Umesh Mishra.
Thank you very much. Can you hear me?
Yeah, we can hear you, sir. Go ahead.
Okay, great. Let me try to share my screen. Okay. All right, can you see my screen? Yeah?
Okay. Yes, we can see.
Okay, perfect. Okay. So thank you very much for inviting me. It's an honor and a pleasure to be part of this first Semicon India. It's a very exciting time for India and for us who grew up in India and wish India all success. It's an exciting time as well. So I'd like to talk about gallium nitride based electronics. My colleague, co-founder of Transphorm, Primit, is going to be on the panel. So I took this opportunity to also talk a little about RF GaN. And Satya said that would be good to do. So here we go. So I'm a gallium nitride evangelist, okay, and the reason I am one is based on a few facts. One is that every semiconductor technology has to be high performance based on application, of course, right? And it has to be very reliable, and it has to have a roadmap for lower cost with every generation. And then, but to have low cost requires very wide market penetration. It needs to be at scale. The previous speakers, I caught the last bit of what they were saying, can't agree more with them. Absolutely you need that. Let me just see. There's something I should not have. Okay. I shouldn't have had animation. It's a bad idea. Anyway, so gallium nitride, more than any other semiconductor, satisfies all these requirements, i.e. high performance, reliable, roadmap for lower cost with every generation, and very wide market penetration. And the market is not only in electronics, it's not only in power electronics and RF electronics, it's actually even in photonics. In fact, the large market today of gallium nitride is in photonics, LEDs and lasers, and of course, many, many other applications. And going forward in extreme electronics, these are niche, but extreme can also be thought about as high temperature electronics, which is something of very great interest now. Now, why is gallium nitride so remarkable? What I'd like to just one quick thing, is it's a dislocated material. That means there's no real gallium nitride. Dinesh will be talking about GaN on GaN, and that is on gallium nitride substrates, but most of gallium nitride is built on a foreign substrate, either sapphire or silicon. And hence you have these dislocations that exist in the material, which reflect the poor quality of the material as far as a material scientist is concerned. But this kind of material actually is the basis of an LED industry, which is greater than 10 billion US. And the same kind of a material was utilized in making AlGaN-GaN HEMTs, aluminum gallium nitride HEMTs, the basis of both power electronics and RF electronics, and is built on this dislocated material. And in the past, people used to say this would not work. You need to use silicon carbide because that's it's a homoepitaxy. It's got a substrate. Turned out that that was not necessary, and we say it's not necessary even today for power. And the reason for that is a material science blessing of gallium nitride. It's a hexagonal crystal, which is of what is called 2C, and it has no stress in the horizontal direction. So the dislocations, even though they're bad, are fixed. And you can always design around something that's fixed. When bad stuff is variable, that's when you die. Anyway, so GaN has broad-based applications. I call it a future-proof semiconductor. Solid-state lighting, our colleague at UC Santa Barbara here, Shuji Nakamura, got the Nobel Prize in Physics in 2014 for inventing this. And this is what got GaN going, but then you have displays and phones, airborne radar, data center power supplies, compact chargers, the electric vehicle, home energy systems now connected to a solar home, solar panels, for example, and of course, rapidly growing 5G, 5G NR, and 6G base station. I just listened to a talk at the rapid growth of E-band backhaul, which is in the 70 gigahertz range in the United States. So this RF part is growing rapidly as well. And but one of the things why I think cost is very important, and the speed of technology development always indicates the probability of success. If something is a struggle to develop, it probably will be a struggle for a long time. And if there is a rapid improvement in performance, yes, you have to work hard on manufacturing, but you have a good chance of it to succeed. This is from IHS, and it says that the rapid adoption of LEDs in lighting marks one of the fastest technology shifts in human history. We have gone from thinking that LED lighting was maybe is going to happen to it's everywhere. And this is the magic of semiconductors. It can scale rapidly, and gallium nitride LEDs has done that magnificently, and it has dropped the cost from relatively high to insignificant now. So let's move on to electronics without waste, because efficiency, efficiency, efficiency is the mantra going forward, be it for RF power or for power conversion. So what is the problem of power conversion? We pay a hidden tax on electricity. In fact, what is the problem? And the biggest problem we have is conversion losses. So the electricity, as it arrives in the outlet or plug point in your home, arrives at 230 volts. AC has to be converted to DC for your laptop, or has to be converted to a different form of an AC to drive your pump for your refrigerator, or so on and so forth. So obviously, you have to have a situation where you're converting 230 volts AC, 60 hertz, to some other form of energy, of electrical power. Those kinds of conversion losses are about 10% of all the electricity generated in the United States. This applies to the US. It's a humongous amount of energy, because that is basically energy that's just wasted, because the conversion process is not useful to us. It just generates heat, and it also entails about $40 billion of economic cost. And it's 318 coal power plant equivalents. This is power that's just wasted in the conversion. And conversion is inefficient, because if you want to just turn something on and off, like the mechanical switch on the wall, that's 100% efficient. But if you then go to, okay, I don't want to just turn it on and off, I want to have a dimmer, and so on and so forth, you always end up with some kind of pulse width modulation scheme to actually manipulate the waveform and change its amplitude. This requires capacitor switching on and off, and when they do that, they flow current through resistors, you end up having loss. So the very fact that you're switching stuff and the fact that you're holding devices on are both causes of loss. What you want is an ideal semiconductor, something that's off when it's off, doesn't take any current, and behaves like a metal when it's on. And gallium nitride actually turns out to be, in my opinion, one of the best semiconductors out there today, for both the ability to deliver power conversion with low losses while doing it at scale and at low cost. So what is gallium nitride? Gallium nitride is when we say gallium nitride, at least folks talking about lateral gallium nitride devices, you basically grow aluminum gallium nitride on gallium nitride. Aluminum gallium nitride is strained on gallium nitride, and this strain actually ends up creating an electron, induces what we call as a two-dimensional electron gas at the heterointerface between algan and GaN. And the reason is the difference in the polar, these metals are polar, these materials are polar. What is polarization? Polarization is an inbuilt charge in the material, just by the fact that the bonds, the chemical bonds in the material are such. So if you put one material with one polarization on a material with another, you end up with a charge which is equal to the polarization difference. So we don't even use doping. And you end up with a two-dimensional electron gas, which has very high mobility. There are two forms of gallium nitride. One is gallium polar and the other is nitrogen polar. And it looks much like a MOSFET. So when you have GaN, aluminum gallium nitride on gallium nitride, you end up with this electron gas, and you have a source and a drain and a gate, and you end up with basically current flowing from source to drain in a material which has very high mobility. So if you look at the mobility of electrons in gallium nitride, mobility is 2000 compared to that of silicon, compared to that of silicon, which is about 100 in the inversion layer. So you end up with, I better switch to my pointer, otherwise it'll keep drifting. So we end up with a material which is all of very high breakdown field. We end up having a breakdown field because our band gap of gallium nitride is 3.4 eV. It's a very large band gap. The breakdown field of gallium nitride is over 3 megavolts per centimeter, and the electron mobility is 2000. It's an amazing combination of a highly conductive material that can hold voltage in the off state. You want the same material. You want the same material to be, when it's off, you want it to behave like an insulator. The fact that gallium nitride has a large band gap makes it that. And when it's on, you want to be a metal. And the fact that gallium nitride has a high mobility makes it that. So, of course, this device is normally on, but in power electronics, you want devices to be normally off. The way we do it at Transphorm is we put a silicon MOSFET in cascode. So you have, to the external world, what the external user sees is silicon, and what's hidden inside is the gem of gallium nitride. So since we cloak the gallium nitride with silicon, it actually gives both the familiarity of silicon plus the GaN advantages in one package. So you have a very simple gate drive, simplicity in device design, and terrific switching performance from the high mobility. And so in the spider chart, gallium nitride, our gallium nitride is in the green, and it's a much better device than, say, silicon in the orange or even silicon carbide. So this high performance gives you opportunities, and I'll talk about the opportunities for power electronics very quickly and leave the rest to Primit. So basically what ends up happening is that when these power conversions, you end up wasting terawatt hours of energy. In industrial moving things around, you waste about 207 terawatt hours. Data server power supply is about 52 terawatt hours, only in the power supply. These are huge amounts of energy. So how much is a terawatt hour? San Francisco in the United States consumes 6 terawatt hours, and New York City, 50 terawatt hours. Las Vegas in Nevada consumes 33 terawatt hours, and this is because of the air conditioning in the casinos, primarily, not the lights. And so if these are the kinds, so you see big urban centers, this is how much you consume. And but what we are wasting is about 300 terawatt hours. So if you use efficient power electronics, you can save that much energy. How much is 300 terawatt hours? Almost all the energy that is used in the Western United States. We waste as much as we use in the Western United States. So the mega trends that are driving growth for gallium nitride are handsets and everything related to, sorry, not handsets, everything related to connectivity, like smartphones and tablets, laptops, gaming consoles, everything like that. Crypto mining is another very big application. Electric vehicles, gallium nitride is going to start playing a major part in this ecosystem. Right now, it's primarily silicon. The second the second person in the second semiconductor is silicon carbide, but gallium nitride is going to come online very soon. And then you have the RF market, which is the infrastructure market. This is growing very fast, and this is in the 5G, 5G NR, 6G space, and defense. Here is a comparison of a normally off gallium nitride FET. Here's the GaN FET. Here's the silicon low voltage FET. It's put die on die, silicon on top of GaN. And here's a comparison of a silicon MOSFET in the middle with a silicon JFET and a super GaN device, our device. And you can see they are all the same R-on, and you see very clearly that the GaN has the least loss, much lower loss compared to the silicon carbide as well, and this is reflective of that spider chart I showed you before. Here's an example of, so yes, gallium nitride is in adapters. We've all heard about how gallium nitride is in various adapters for fast charging. It's a very big market, and it has allowed GaN to penetrate. But GaN is not stuck in these low watt markets. Here's an example of us gallium nitride in a 3.6 kilowatt titanium class crypto mining power supply, which has a peak efficiency of the full supply greater than 96.4%, making it titanium class, driven by gallium nitride in what is called a totem pole PFC circuit. So gallium nitride is in power supplies, it's in scooter charging stations. This is an example of gallium nitride powering some of Gogoro's battery swapping stations in Taipei. So now let's move on to RF. So RF opportunities are huge. Same things that give us good power conversion gives us good RF. High breakdown field, high velocity, high charge in the channel. Charge gives you current, and the high breakdown field gives you voltage, and the product of current and voltage is power. So you can always get great power out of gallium nitride. So let me state it another way. A transistor for RF needs gain, an amplifier needs gain, otherwise who the hell wants the amplifier? Large signal gain because you're driving it with power. And this gain requires, to get high gain, you need mobility, velocity, and you need large current swing. This comes from the charge in the channel, large voltage swing, that comes from the breakdown field. And you basically, for output power, you also need high gain. So this feeds into that. And you need efficiency, 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 efficiency. And for that, you need high output power and high gain. All right, so gallium nitride gives you all of the above. That's why gallium nitride is able to serve multiple markets. Remember what I said in the beginning. If it's a niche technology, you're dead because you're never going to make it cheap. So between LEDs, power conversion, and RF, gallium nitride has a wide swath of applications which it can serve. And right now, what is becoming really hot is SATCOM, the defense sector, of course, and 5G, all right? Here's the history of AlGaN HEMT. We at UCSB, at UC Santa Barbara, showed the first microwave power performance of an AlGaN GaN HEMT in 1996. And it went from 1 watt per millimeter to 4 watts per millimeter. Then we introduced silicon nitride passivation, not only us, Santa Barbara, Cornell, Cree at that time. About the same time, we introduced silicon nitride passivation. That passivation got the power up to 10 watts per millimeter. Then at UC Santa Barbara, we introduced the concept of a field plate, and which basically spreads the electric field. And that got us from here to 25 watts per millimeter. And then at Cree, by using multiple field plates, we ended up showing 43 watts per millimeter. Remember, I told you if technology improves fast, then you have a good chance of developing a terrific technology. And here from 1996 to 2006, in 10 years, you went from first demonstration to obscene amounts of power. Of course, we can't use this much power because the heat associated with delivering this power is hard to manage. So typically today, people use highly reliable 5 watts per millimeter device. Here's an example of linearity. Linearity is very important because if you have a highly linear device, you can jam your customers very close together within a bandwidth. And this means you make more money. If you basically have poor linearity, you have to separate your customers in frequency, you lose money. So basically, highly linear devices are important. Gallium nitride is a highly linear device, and with digital pre-distortion, can be made even more linear. Its market right now is about $700 million, growing in 2019, growing to about $2 billion in 2025. And look at this mix. It used to be all defense, okay, 7 years ago. Now it's more wireless infrastructure than defense. SATCOM is starting, and CAT-V is also a big market. Millimeter wave applications, I'll finish with this in another, it'll take me another 5 minutes. I hope I'm not running out of time. E-band radio is a very big area. This is part of the backhaul system for very high bandwidth and to really move data. This is growing very fast. This is in the low W band range, okay, 70 to 80 gigahertz. So that's basically just at the corner between E-band and W band, okay? And then, of course, there are in millimeter wave to the handset, people are doing that at Ka band and even low down at 5 gigahertz. So communications is happening from 2.6 gigahertz all the way up, even today, up to 70 gigahertz. All right, the 70 gigahertz is for backhaul, but the handset, of course, is still in the sub 5G range. Automotive radar is already in the 30 gigahertz range, going to 79 gigahertz. Now, why is at millimeter wave, gallium nitride plays a very big role? Why? Because at millimeter waves, when you basically have an array, and when you have an array to deliver power, the distance between elements is about lambda by 2. So you have, and since lambda is getting smaller at higher frequencies, you've got to jam. You don't have space to put these elements, and so each element has to put out more power. So you need more watts per millimeter. So, but what happens is the watts per millimeter from devices, gallium polar devices, plummets as seen here. And at very high frequencies, you don't get many watts per millimeter, and you definitely don't get it at efficiency. So what we did, and here's an example. In 2016, Raytheon, a very good company in the United States, showed that they could get 7 kilowatts at 95 gigahertz by combining 8,000 ICs, and you needed a crane to lift the damn thing. Recently, as in this month, they published a paper last month where they showed this is a 100-watt W-band 94 gigahertz PA from Raytheon, but again, the wall plug efficiency is only 6%. Why? Because the power added efficiency of these elements is about 15%. This is a heroic demonstration, but everybody, and they also agree, we have to raise the efficiencies. So how do you do that? So what we developed at UCSB since 2006 is a new form of gallium nitride called nitrogen polar GaN, which is, instead of having AlGaN on top of GaN, we put GaN on top of AlGaN. It's an inverted structure. It's very easy to draw, very hard to do, but we did it over the last 15 years. And these nitrogen polar structures basically have regrown contacts for low resistance, a gallium nitride cap to reduce dispersion. It also, by polarization, it turns out, also reduces the resistance of the channel which you modulate, so gives you more current. And so when you get high gain, high breakdown voltage, low leakage, and low parasitic resistance. Why do you get high gain? Because in this particular structure, the AlGaN back barrier is what is called modulation dope. We put silicon atoms here, we get electrons here, and we can put the gate next to the channel, and we decouple the distance between the gate and the electrons from the design of the device. This is very important because this distance has to be small for very high frequency devices. Well, when you put all this stuff together, what we managed to show at UCSB that we got 8.8 watts per millimeter at 94 gigahertz, an unheard of number. And for anybody in the audience or listening in from on their computers, 94 gigahertz, 8 watts per millimeter was considered nearly impossible even just a few years ago. Not only did we get it, but we got the high density, we got it at high efficiency, 27% power added efficiency at 94 gigahertz. Recently, my student got 5.3 watts per millimeter, which is extremely good, at 35% PAE. These numbers are insane when it comes to 94 gigahertz power. And since the device is well designed, this is the only device in the world that shows the same device. You can measure at 10 gigahertz, 30 gigahertz, and 94 gigahertz, the same device, and it gives you the same watts per millimeter at every frequency. This is what theory tells you should get. Watts per millimeter is not a function of frequency, watts is. So basically you end up at, what changes of course is efficiency. So we have 27.8 efficiency at 94, we have 59% power added efficiency at 30 gigahertz. So I'd like to just conclude with one statement. Gallium nitride, just to put everything together, gallium nitride is a magnificent material. It puts out light. It is changing the world, the whole world of lighting and displays. So many applications, okay, on the photonic side. I haven't even touched that. I mean, I could give a whole hour lecture on just that because it's so amazing. Now, following that, we have the second wave, which is basically RF and power electronics. Power electronics is a much bigger market than RF, but RF electronics is also growing extremely fast because of communications, and now we have one material system that can cover all the way from C-band, 4 gigahertz, up to W-band, 94 gigahertz. And that is really fascinating. So I think that it's going to become a dominant semiconductor, and what follows below is the word exponential. The gallium nitride lighting industry is growing exponentially. The micro and milli LED display markets is now emerging, but is going to grow exponentially for virtual reality and augmented reality. RF industry is growing exponentially. Power conversion is going exponentially. And GaN on silicon and sapphire gives a pathway to low-cost devices, which will drive broad adoption. And new markets are emerging on the photonic side. UV LEDs is just exploding with some new breakthroughs, and that is leading to like disinfection, especially in the time of COVID, and has driven this, and the technology has met the moment, and there's going to be a whole new area of growth in this sector. So I thank you very much, and I hope I didn't run over time. I'm happy to take questions.
We'll just take one question. We'll just take one question. Yeah, here. Yeah, we'll just take one question. Sorry, because we're already running behind schedule. And if there is a quick question, yes. Yeah, quick one, sir. Yeah.
Hello. Yeah. Professor Mishra, I think it was a beautiful presentation. I really learned a lot, got great insights. My quick question is, what is the current market share of the gallium arsenide, and what is the trend, the way you have projected it is going? Any ballpark figures, like today it is 10% growing in next 5 years to 50, whatever?
Yeah, so basically currently on the RF side, the gallium arsenide in the base station for 5G is completely gone. Okay, all 5G is switching to gallium nitride. So the all new deployment in 5G is gallium nitride on the infrastructure side. So that's a complete switch that's happening. So it'll be 100% GaN. In defense radar, it's also switching. So all new radars are starting to be built with GaN. But legacy systems in defense will remain gallium arsenide for a long time. And in the power sector, of course, it's 95%, 98% silicon at the moment, and gallium nitride is literally in the single-digit range, small single-digit percent range. So the growth potential is huge in power electronics.
Thank you.
Thank you very much, Professor Umesh Mishra ji. You've taken time off, and gave us a wonderful keynote. Thank you very much, sir, for joining us.
Yeah, I appreciate it. Thank you.
And now